It can look like a million different things. So this is what happens when you change your mean. It just shifts your bell curve to the left and to the right. So this is the same standard deviation, but different mean. So that's all that happens when we're talking about transformations of your bell curve, is that if you change your mean, it's just shifting your bell curve left and right. Whereas this is the same mean, so we're still centered around the same number, but different standard deviation. So this was a standard deviation of 2, 5, and 8. So the smaller your standard deviation is, the more like thin and very clustered your bell curve is, versus the further it's spread out, like the lower your bell curve gets, the more spread out it is, and that means that your standard deviation is larger. So yeah, this is, congratulations, normally distributed. You'll see it all the time in statistics when somebody tries to present something in statistics, when you're talking about presenting data, when you're talking about presenting things for politicians or in the news, you'll hear quite frequently this idea of like, well, it's normally distributed. The curve that we do for your IB exams are forcing your tests into a normal distribution curve. That's how the IB does your curve, is that we say, okay, well then 65%, the middle 65%, then have this grade. And then there should be like only a few who get slightly above and a few who get slightly below. And so it kind of forces us into this idea of a normal distribution. And that's how IB curves work. So it's something that's prevalent everywhere. And now you know a little bit about what it means to be normally distributed, which is cool. All right, we're gonna do 2 examples together, and then that'll be it. The heights of young German men between 18 and 19 years of age follow a distribution that is approximately normal, with a mean of 181 and a standard deviation of approximately 8. So we're going to assume that we've been told that it's been normally distributed. We've been told that the mean is 181. And we've been told that the standard deviation is 8. It then says to describe the population of men, and that's a really vague question, but what it's asking you to do is it's asking you to understand what it means to be normally distributed, and then to verbally describe that graph. So if we had a graph like this with our bell curve somewhat like this, we've got our mean here at 181. And then we just kind of say, well, I don't know, something like this is a standard deviation away. So this is 1 standard deviation away. So we would add the 1 standard deviation of 8 to 181, which becomes 189. Subtracting it from 181 becomes 173. Mental math, it's late at night. So that is 1 standard deviation away from your mean, which means it's representing 65% of all of your data. So that is one description that you can do for this graph. 65% of young men are between 173 and 189 centimeters. Oh, that's a little too many bumps there. Oops. So that's one description that you can do. And then to continue with that, we're going to add another standard deviation. We're going to add another 8. So 189 plus 8 is 197. 173 minus 8 is 165. And then we know that that represents 95% of our data just by using the empirical rule. So that means that 95% of young German men are between 165 and 197 centimeters. The last one, we're going to add one more standard deviation, and this is representing the majority of our German teenagers between 18 and 19. We're going to add another standard deviation of 8. So 197 plus 8 would be 205. 165 minus 8 is 157. So we can say 99.7% of young German men are between 157 and 205 centimeters. That's all you need to do to describe it. If you wanted to talk about like the small percentage that are outside in these tiny little tails, you would then subtract 99.7 from 100, and that's like 0, it's 0.3. But if you, I think it ends up being like 75, and so you talk about 0.25% being outside of that scope, less than 157 and greater than 205. So a very small percentage, but that's going above and beyond. This is like the main thing that it's wanting you to do when it says like, hey, describe the situation. This is what you would say. Let's talk about how we calculate now, because you now are also doing calculations. The probability that the mean of a person whose height of a man between 18 and 19 has a height between 173 and 189. So we've already talked about the fact that 65% of these men are between that. But we have to realize that 65% is an approximation. Because it depends on what your standard deviation is. It depends on what your mean is, that like things are going to slightly change around 65, but it's going to be about 65%. So we can actually do the calculation to know how many are between that. And we'll use our calculator to do that. So how we find this on our calculator is that we go to menu and we go to distributions, which is, or sorry, probability, which is 5, and then distributions, which is 5. And then we want to do normal. Realize that PDF is at one value versus CDF is cumulative. So if we're talking about between 173 and 189, we're going to do our cumulative distribution. And we're mostly going to be doing that distribution when we're talking about normal, because it's pretty normal with normal distributions that we're going to be talking about between certain values, because we want to find the area underneath that curve. So normal distribution. So type out that process. We go to menu. We go to 5, probability. We go to 5, distribution. And then we go to 2, which is normal, C, D, F. I'm pretty sure if you have a TI-84 that normal distribution is close by to what your binomial distribution was, just like this one is for our TI Nspire. So hopefully that'll be easy for you to find. If not, you know the drill. Okay. So our lower bound on this guy is going to be 173. Our upper bound is going to be 189. Our mean is 181, and our standard deviation is 8. We get 0.683 as our probability. The probability of being between 173 and 189 is equal to 0.683. So 68.3% represents the population of German men, young men, who are between 173 and 189 centimeters. So close to 65. So this is where we see that 65 is an approximation, but we consider it to be a good approximation. But we have to make sure that in our language we use things like it's approximately 65%, because it's really actually 68.3. Okay, last problem. The length of trout in a fish farm are normally distributed with a mean of 39 and a standard deviation of 6.1. I really like to represent these with variables just to like have it easily accessible, right? When we want to go back and be like, wait, what was the standard deviation again? I don't want to read a whole sentence because I'm lazy. I want to just be like standard deviation, boom, 6.1, move on. We're going to find the probability that a trout caught in the fish farm is less than 35 centimeters long. It says that it's normally distributed, so we can assume, or we can move on with that knowledge that it's normally distributed, and we can use that in our calculator. We want to do a cumulative distribution because we're going to be between, if we want to be less than 35, the probability that X is less than 35, we're going to be between 0 and 35. There's really no discussion about less than or equal to with our cumulative distribution, or our continuous distribution, our normal distribution. If it's less than or equal to, or just strictly less than, it's the idea of like the area under the curve. If you moved it over by a hair, the area would still be about the same, right? If you moved it over to include 173 or to not include 173, the area under the curve is pretty much exactly the same. You're still talking about this whole area, and you maybe added just a tiny bit, but it's small enough that it's negligible. So we're going to put 35 into the calculator, average 39, standard deviation 6.1, and we get 0.256. And that's it.